And dear friends, welcome back. Welcome back to my YouTube channel. In today's short video, I'm going to tell you how does Abacus help you in evaluating material behavior, or in other words, how does a model, that material model that you're using in Abacus, how does that fit your data that you are making as an input to the model? So sometimes what happens is you do not have all the material parameters or the constants that are required to to be input to the model. So what you do is you have some experimental stress strain data, or you do some experimental testing to get stress strain data, and that then you input that in particular material model. So how does your input, that is a stress strain data, how is that being used by the model? Is it the similar way that you are inputting, or is there something else, or is there a way to evaluate all the required constants using that stress strain data? It's This approach is mostly used and very helpful in when we are using elastic models that are available in Abacus. Let's say, for example, uh, in the material tab, if you go into mechanical and elasticity, there are a lot of elastic models. There's a there's a conventional elastic model, there's an hyperelastic model, hyperfoam, low density foam, hypoelastic, porous elastic, viscoelastic. These are all elastic models, and this approach is very useful when we are using these elastic models that require a lot of constants to be evaluated, and that also have a provision of incorporating stress strain data. Let's let's talk about hyperfoam. So if I go to the stress, uh, firstly I would define density. Let's say I have uh, I have already tested a hyperfoam that I know it has a density of, suppose, 120 kg per meter cube. So if I'm using mm and Newton units, so I have to put it like 120 e power minus 12. So to be very consistent with the units, but that's not the purpose of this video. We are here just trying to see how do we evaluate different constants using stress strain data. So let's go to the mechanical. Let's go elasticity. So I'll use hyperfoam because I have the hyperfoam stress strain data that has been experimentally evaluated. Here's when I go hyperfoam, and if I'm going to use this hyperfoam model in my simulation, or like do different, or to simulate the behavior of any foam material, I need three constants: mu1, alpha1, nu1. You can refer to this model in the Abaqus manual. You will get what do these constants mean. So if you are using, there's something called strain energy potential order. If you're using one, you'll need three constants. If you're using, suppose, two, because sometimes to better like fit the model, you may need six constants. If you increase this, that will might increase the accuracy. If you're going it for three, so you will need nine constants: mu1, alpha1, mu2. Similarly, uh, alpha2, mu3, alpha3, nu1, nu2, nu3. So what we'll do here is, let's stick to one. But since suppose I do not have these material constants, I want to evaluate them. Or first, on the first hand, I want to use stress strain data. How do we do that? This model, and like many other elastic models, it gives us a provision of using test data. So when I am checking on test data, I'm getting a dialog box like this. And in the test data, I've already done uniaxial testing, and the stress strain prove that I have got in my experimental date, those experimental testing, I can just substitute it here. So what I'll do, I have stress strain data of the hyperform. So this is how the behavior of the form here is. You can just Google the behavior of hyperforms. It's something like this. There's an initial elastic, uh, linear region, then there's a plateau, then there's again a peak. So it has a lot of mechanics into it. I can copy this. Since this is a compression data, this compression data needs to be using this hyperform model. This needs to be in the negative uh, sense. It has to be input in, like, both stress and strain needs to be negative in negative numbers. So I have copied it, and I will go to my this material tab, and then I will just paste it here. So I have pasted my stress and strain data. I'll click on OK, and that's it. But when I'm clicking on OK, but does it really fit it the way it is? We have already looked into how does the behavior, causostatic behavior of this hyperform looks like. So it's something like this, and the peak value is around 4, right? So let's say let's see, there's a provision of evaluate here, and that's available mostly for the elastic models. When I'm clicking on evaluate, it gives me, what do you want? You have a standard test done. That means uniaxial test you have already done, and the minimum is with respect to the, like, since this is negative, that's why it's calling as a minimum. I'll say the minimum strain there is 0.8. If you see here, it is 0.8. It has compressed up to 80%. So I can define it here also. My minimum, or the maximum strain, in other words, will be 80%. Have I done the biaxial testing? No. Planar? No. Simple shear? No. Let's say I only have this compression test, and it will read it as compression because I have given it as negative stress strain. So test data. I want to just see how good the fit is. I'll say okay. I'll have to wait since it's now evaluating the model. It will show me the original stress strain data and uh, original stress strain curve and the fitted model. So here it is. We are almost done. Yes, here it is. This red is the, if you see test data, and it's up for, and the blue is the this hyperform model that I have used. So you can see, if I just go on like analyzing my form using this hyperelastic model here, so it's not going to give me the correct response because the model itself has fitted it in a different way. So the model is going to use this blue line. So what can I do is, let me go back to properties. Let's say, suppose again I'll go to material 1, hyperform. I will use strain energy potential as 2, higher. Let's see how improved my response becomes. Evaluate. Yeah, it's relatively better because it's not making a zero slope here. It's relatively better. If we increase this strain energy, maybe strain energy potential, you can just go through the theory and see how what does this strain energy potential order means. I can go to 3, I can go up to 6 in maximum. So I'll go for 3 and then evaluate the material model again. It's still being evaluated. It's taking a bit of time. So please bear with me. Yeah. So here it's a lot better. There's a there's an elastic region, or rather a linear region. Then there's a large plateau, and then there's an increase in the nominal stress. So I can take the risk of rather using this model. This may give me approximately a like a and like far better response than we saw earlier. So this is how we can just compare the two models. But let's say I'm still not satisfied, and maybe higher order strain energy potential this order also like doesn't give me the like proper results. I want to evaluate the material constants. That's mu1, mu2, mu3, and play with them. So how do we do that? Again with the properties. I perform. Oh, this is done. I don't need to do anything else. But I can just reduce it not to 3. I'll say let's use 2. So I need 6 constants rather. So I will evaluate all the 6 constants. In the evaluate here, source don't sit as data. I'll say, or no, rather it's okay. Test data. Okay, it's the same I'm repeating, but here we will look into a file that is generated that shows us the constants that the model has evaluated out of it. Here I have got all the. If you look at this file, it gets generated simultaneously when you get to see these plots. So material name is hyperform. So we have set n equal to 2. So it is evaluated mu1 alpha 1 this new one, and we have total 3 constants here, 3 constants here. And now if you're not satisfied with this plot because it has evaluated these as numbers, you can play with the numbers and make a best fit, and then you can proceed with the same. I hope you liked it. So with any other elastic model, you can do the same. You can evaluate the material parameters required. Since I have used only uniaxial compression test, that's why maybe the fit is not as good as it should. Thank you so much. Stay tuned for more videos. Thank you.